Hello and welcome back to our image and video processing class. This is our second week of class and we are going to talk about image and video compression, which is probably one of the most successful areas of image and video processing. Compression is used all around and is actually an enabling technology, as we are going to see. If you have some background in information theory or previous background in signal processing, some of the topics in this unit will be easier for you. But if you don't have background in those areas, don't worry, because the unit is going to be self-contained and I'm going to teach you about the concepts that you need from those areas of information theory and signal processing so we can basically understand how image compression, JPEG, MPEG, and other technologies work. So let's start by illustrating why do we need image compression. This is not too hard to explain, so let's just do some numbers. Let's just think that we have an image that has 1,000 by 1,000 pixels. We know this actually in today's standards is actually what we call a low resolution image. But let's just use it for the sake of some numbering. And let's just assume that we need 8 bits, as is normally standard, 8 bits to represent each one of the colors, which means that we need 20 bits per pixel. So we have an array which is 1,000 by 1,000 and 20 bits to represent the 3 colors. So this is one image, and if we are doing video, it's just one frame. We actually need 30 of these to get 1 second of video. We get 60 of these to get 1 minute of video. And then we have to multiply by 120 to get basically about 2 hours of a regular movie. So what's this? The result of this is a very large number. Very, very large number. And you can do offline the computation, but you're going to basically agree there's a very large number, even for a relatively low resolution image. So if we only have one image, we still have a very large number here. And we won't be able to basically save a lot of these images in our cell phones or in our computers if we don't do compression. So the moment we start talking about images and video, we immediately get very, very large numbers, and that's why we need image compression. We need to make possible to save those images, to save those videos without occupying so many bits in our computer or in our cell phone. So that's the reason we need basically image and video compression. The question is, why can we do image and video compression? And there are many reasons, and we're going to talk about many of them. So one of the reasons is what normally is called coding redundancy. And that's one of the first things that we are going to see, that not every pixel value is equal. Some pixel values appear more, some pixel values appear less. As we can see in this image, there is a lot of the gray values representing this star, and only a few representing these white lines, and maybe none representing certain colors. So we actually see that there is 1, 2, 3, 4 colors here. So if this is represented with 8 bits, it's kind of a waste to use 8 bits, 256 possibilities to represent 4. So we're going to exploit that. There is another reason that we can do compression, and the reason is a lot of redundancy. And this is illustrated in this image. So let's assume that one of these lines has a constant gray value. Let's just say 128 for the sake of the example. And let's imagine that this line is very, very long. Let's assume 10,000 pixels. So there are 2 ways, at least, 2 extreme ways to basically represent this. One is to 10,000 times, say, 128. That will take us 10,000 bytes, or 10,000 times 8 bits. So we're going to say 128, 128, 128, 128 for 10,000 times. That looks like a lot of waste. On the other hand, if I say, starting here, I say 10,000 times 128. So I just give a number that says how many times I'm going to repeat 128. That's much smaller amount of memory to save that. I need to save the 128, which is the pixel value, and I need to save the 10,000, the number of times that 128 appears. And that's certainly much less just saving those two numbers than 10,000 times saving 128. So this is an extreme case, but a very important, and this happens often in images, that we have uniform regions and basically some geometric coherence in the image that we can exploit to do compression. So that's the second reason we can do compression. And that also happens, by the way, in video, as we are going to see. The third reason we can do compression is right here. This is a flat image, constant value. So basically, there is a lot of irrelevant information in images. There's a lot of information that we actually don't care to save, or we don't care to save in a slightly different fashion. For example, if this is 128, maybe I don't care if I tell you it's 127, okay? Or maybe I don't care of it at all. So I might not care about its exact value. I might not care too much about the information at all. So there is a lot of unnecessary information which is irrelevant. So these are the three reasons that we can compress. And we're going to exploit all these reasons, and then we're going to get very large amounts of compression. There is a lot of compression, as I say, in the literature, and part of the success of image compression is that it became standard. And that's very important, because if I save an image in my digital camera, I want every computer to be able to read it. I want to email it to my friends and colleagues, and I want them to be able to read it. So the way I save my image has to be compatible with the way that others read it. And that's why there are so many basically compression standards. In still images, these are three of the most popular. Of course, you know a lot about JPEG. JPEG is what basically most digital cameras use, and it's going to be basically the way that we are going to teach a lot of the image processing, image compression in the next hour or so. There is JPEG-LS, which does what's called a lossless compression. So exactly what you see is what you compress. So in that case, there is no irrelevant information. Everything will be compressed. And there is the new standard JPEG 2000. So we're going to talk a lot about JPEG and JPEG-LS. In video, there is also standards. So once again, when I take a video, save it on my phone, and send it to my friends, I want them to be able to read it. For that, they need to know how I did my compression. And of course, the most common ones are the MPEG family, although there are other techniques as listed here. So it's kind of a two-sided street. Image and video compression has been so successful that it made it to standards that everybody uses the same techniques. And the fact that everybody uses the same techniques also made it very, very successful and very popular. Now, digital camera manufacturers can with confidence basically use JPEG because they know that everybody will be able to read it. And that's why they are comfortable using it. General image compression techniques that exploit all the types of issues that I mentioned a couple of slides ago work as follows. So you start from the image, and there is a mapper. So we take this array that we talked in the previous week of, let's say, 1,000 by 1,000 points, and we transform it in a way that is more friendly to compression. And we're going to talk about these maps. Some of these maps are going to be related to Fourier transforms. It's actually a cosine transform. Some of these maps are going to be actually in the spatial domain, just looking at neighboring pixels. We're going to talk about that. Then after that mapping, which basically brings the image into a space friendly to compression, there is quantization. We have already talked about quantization. Quantization is the main step that introduces error, that introduces something that helps the compression but limits me from being able to reconstruct exactly the image. So for example, we might have a pixel value, as we saw last time, about 17, and my quantization technique might say that I need to divide by 2 and basically round it to the closest integer from below, and then multiply by 2, something that we talked last time. So I will end up with reconstructing, instead of 17, I will reconstruct 16. So I introduce error by doing quantization, and we're going to describe some of the best techniques to do quantization, and actually also the quantization that is used in JPEG, which is basically of the type I just wrote here. The last part is the symbol encoder. Okay, I have done my mapping, I have done my quantization, now I have a value in my hand that I need to transmit. And I want the receiver on the other side to get exactly that number. That's where information theory comes into play, because information theory tells us how to do this very, very efficiently, both in computational time and to achieve compression. This is the one that's going to basically exploit the redundancy that there is in the image from the point of view of using some pixel values more than others. And we're actually going to start from this, that basically says, now I have done everything I need to do to my image. I want you to store or to transmit that pixel. Then, once you have compressed the image, you basically have a file with a compression. That's the encoder, the one that takes the image and compresses it. The decoder will basically decode the symbol. It won't do basically a quantization, because the quantization is done at the encoder. It might reverse it, for example, multiplying back by 2. And then it will do the inverse of the map, and it will give you an image that might be the exact image if this is a lossless compression with no error, or it might be an approximation of the image, very often an approximation that we cannot with our naked eyes actually realize the difference. So it would be a great approximation like in JPEG or MPEG. So that's basically the whole steps, and this also explains why we need standards. If I use certain mapper, the decoder needs to understand the mapper so he or she can invert it. And I need to explain to the decoder the symbols coding that I use so the decoder can do the reverse of that symbol coding. JPEG is an example of this, and as I say, we are going to basically explain how JPEG works. JPEG takes an image and divides it in sub-images, meaning it will take a whole image and will divide it in blocks. In particular, these blocks are going to be 8 by 8 pixels, and we're going to see why is that. Then does a transform. This is the mapping we just talked. In this case, it's going to be a discrete cosine transform, and we're going to explicitly talk about it, write down the formulas, and explain why this is a transform that is used. It's going to do quantization of the type I just mentioned. Basically, JPEG is going to divide by a number and basically round it. Okay? It's going to divide by different numbers. There's going to be some adaptation that we're going to explain. And then once it has done that, it's going to do a symbol encoder, which is a Huffman code, which we're going to explain as well. But this is all what is done in JPEG. And you're going to see one of the optional homeworks I give you for the end of this unit is actually to implement JPEG in your computer. It's not very hard, as we're going to see, and that's part of the reasons this algorithm is so successful. The decoder is going to decode this, it's going to do the inverse transform of the DCT, it's going to put the blocks one next to each other, and it's going to show you the image. Okay? And we're going to talk, this is done for one color. We're going to also talk how the different colors, the RGB, are basically exploited. Also, by basically using some redundancy between the colors, we can actually get even more compression. So JPEG is basically an example of the prototype of the techniques of image compression with a mapping, that is this part, a quantization, and a symbol encoder. So, and a very successful example of this technique. So I think it's time now to basically go and talk about each one of these blocks in detail.